To teach a machine human language, you cannot treat words as isolated, discrete tokens. You must map them as coordinates in a continuous geometric space. You have likely seen this equation: king minus man plus woman equals queen. But there is no explicit rule telling the machine how gender or royalty works. That relationship is an emergent property of vector dot products. Despite its fame, Word2Vec is often described through the lens of a major misunderstanding. Practitioners frequently treat its two primary models, continuous bag of words and skipgram, as two separate neural networks. These are actually inverse predictive training objectives operating inside a single, unified parameter space. Many learners also assume that the standard softmax function, the purest version of the model, is what actually runs in production environments. In reality, the naive formulation is computationally intractable at scale. Training it on billions of words requires a specific mathematical rescue operation to function. To master modern language models, we have to trace how this unified architecture and the optimization known as negative sampling generate meaning from raw text. Let us build the framework from scratch. We will use a microcorpus with a tiny 8-word vocabulary and set our embedding space to 3 dimensions. Notice our network's 2 weight matrices, input to hidden W and hidden to output W prime. In continuous bag of words, blue lines average surrounding context vectors to predict one target word. Skipgram uses one target word to predict multiple context words. The center nodes remain static. Word2Vec is a flexible family of predictive objectives utilizing the exact same architectural geometry. But if we scale up this architecture exactly as it is built for the real world, it completely fails at the output layer. The softmax function normalizes probabilities and dividing the target word score by the sum of scores for every vocabulary word. In a real-world vocabulary, calculating this denominator requires computing gradients through 30 million output weights. Almost all compute is wasted on 99,999 irrelevant words. Executing this full computation for billions of words is impossible. The mathematical formulation requires a drastic optimization to survive training. That optimization is negative sampling. It completely abandons the multinomial softmax function. This shifts the problem from predicting one specific word out of 100,000 to a binary logistic regression. It asks a much simpler question: is this a true target context pair or random noise? The new objective maximizes the dot product of the true word context pair while minimizing the dot product against k randomly drawn negative samples. Instead of updating 100,000 vectors, the model updates exactly k+1 vectors per step, significantly dropping the computational burden. However, drawing random noise words uniformly from the vocabulary fails to provide useful negative boundaries because the model rarely encounters common words as negatives. To solve this, noise words are drawn from a specialized distribution where the raw unigram word frequency is raised to the fractional power of 3/4. This dampening mechanism forces the model to separate true meaning from hyperfrequent filler words while still building precise vectors for rare vocabulary. This chart shows the empirical results of this optimized training loop. These oscillating data points represent the direct visual footprint of negative sampling, constantly contrasting true pairs against random noise to carve out the geometric space. Negative sampling is the mathematical engine that allowed embeddings to scale to the entire internet. With the math solved, we can inspect the actual geometric space the model constructed after training. This cosine similarity heat map displays our microcorpus results. Values near 1 indicate strong geometric alignment. The model grouped eat, eggs, and daily together based on their co-occurrence. But notice the 0.97 correlation between orange and I. Semantically, this is incorrect. On tiny datasets, Word2Vec strictly captures local physical proximity. It shows that the model identifies patterns of co-occurrence rather than linguistic meaning. Meaning in artificial intelligence is an emergent geometric property, driven entirely by prediction and contrast. By shifting from frequency counting to predictive modeling and utilizing negative sampling to manage the scale, Word2Vec laid the mathematical bedrock for every continuous vector space and modern transformer architecture in use today.